Hi everyone. So today I'm going to be taking you through the final project that we have made for our deep learning course at IBA for the semester of fall 2022. The project was done by me, Omar Ahmad Khan, and my partner Wasila Rehman. So the project was essentially to compare the performances of different sorts of autoencoders by testing out different hyperparameters and passing various data sets through them. The first thing that I'm going to do is that I'll be taking you through the data sets and introducing you to those. So the first data set that we used was that of a Tetuan city power consumption. So Tetuan is essentially a city in northern Morocco, and this data set essentially gives us how much power was consumed in their three different power zones: zone 1, zone 2, zone 3, given these five different variables: temperature, humidity, wind speed, general diffuse flow, and diffuse flow. The second data set that we used was that of bike sharing data. So essentially, you know how a lot of the advanced cities have different bike racks across the city from where you can go rent out a bike, take it to another part of the city, and re-rack it into a different rack. And you're going to be charged according to how long you had the cycle or for how far you rode it. So in this case, the data set is the essential thought process behind this is that we will be able to predict a lot of the happenings around the city just based on this data, from figuring out how long it took from us for a week cycle to go from one stand to another. And to do this over here, to do this, they give us a lot of different features. Over here, I've only defined a few of them, such as seasons, holiday, weather set, etc. So these ones that I've defined in this description are only due to the fact that these are encoded data labels. So one refers to winter, two refers to spring, three for summer, four for fall, so on and so forth for different variables. The third data set was that of a combined cycle power plant. Now, this data set had 9,000 plus data points, and essentially it gave us essentially it was a data set of around five features, four of which were your x-axis. Those are the temperature, ambient pressure, relative humidity, and exhaust vacuum. And these four data points were used to assess what your net hourly electrical energy output would be of the plant. The fourth data set that we used was gas turbine emissions. So over here, it gave us a lot of similar information to the first one. So it gave us a lot of readings from your surroundings for ambient temperature, pressure, etc. And our job in this was to essentially figure out either what the carbon monoxide emissions are or the nitrogen oxide emissions are. And lastly, the data set that we used was for Korean apartments data. This was the only data that we got off of Kaggle. The other ones were from the UCI repository. So the Korean apartments data set essentially gave us a rundown of 10 years worth of sales of Korean apartments. And it gave us their sale price against all of their different. Basically, it gives the rundown of how different factors affect their sale price. And our job was to understand that relationship. And then carrying on, we thought that it would be a lot easier if we could just build different pipelines to pass all of our data through. Now, that data would basically, the pipelines would be such that we will pass a single data set through that, and that data set will be carried on and it will learn. It will be passed on through different sorts of autoencoders, and using that we will be able to assess how well each autoencoder has performed on that specific data set and then compare those later on. So first you can see is that I initialized an empty list of called datasets, and then I appended all of the files that we're going to be using into that list. This was only done for easier assignment later on. Over here, as you can see, I've done df1, df2, df3, df4, df5. These are the five variables that I've assigned for the five different data frames, and these are the respective uh, items on the list. Okay, so the first proper pipeline that we made was that called ML models, which would basically take in any data frame, and using that data frame, it's going to take the last column as your y-axis and the rest of the columns as your x-axis, and is going to perform a train test split on that. pass it through a linear regressor, find out the mean square error as the model AUC1, and then pass that same train test split data through a random forest regressor, find out the mean square error for this, and return both uh, error values as the output of the function. Next up, we defined two different functions over here. One was to calculate your JS divergence, and the other one was to calculate your KL divergence. Both of them take in three values. The first one is the predicted vector. So this is a vector of all the values that your regressor has predicted. And the second one is the actual vector. So these are the actual values of all the instances. And then there's the number of samples which you can use to figure out exactly how great each divergence is. Now moving on, basically we coded a lot of different sorts of autoencoders, the first one being the baseline autoencoder. This one we kept very simple. The input and the output are the same shape. So essentially the input and the output both have equal number of neurons to the number of features in the dataset. For encoding the data, we only put in one layer called encoded with 32 neurons, which is taking in the input from the input layer. The bottleneck is of a variable dimension. This is made variable so you can test out different values such as 1, 2, or 3, whatever is needed later on. And it's passed through a sigmoid function with the encoded data being brought in. And then that from the output from the bottleneck is sent on to the decoded layer, which also has 32 neurons, and then that is finally passed on to the output layer. So that is essentially our base autoencoder. So once it's compiled, it runs the data set through a lot of different tests, and it figures out all the metrics that we're going to use to compare all of the different mm, models and data sets going forward. These metrics are training loss, validation loss, RMSE, JS divergence, scale divergence, and then you also have the multiple linear regression scores and the random forest regressor scores, and then the model name. The model name is essentially just used to identify uh, what model we're referring to with the scores that we're going to be appending. And then after that's done, it also ends up plotting a graph which is going to be your loss values for your training data set versus your testing data set for each data frame and on each autoencoder. The next autoencoder that we coded in was a variational one. Now, variational autoencoders are ones that essentially try to learn the distribution parameters at the bottleneck. So in this case, it's going to be learning exactly what encoded information is coming into the bottleneck. It's going to learn its distribution parameters and then try to generate different outputs based on that. So in this, we can see that there are three layers for encoding the data. The first one having 128 neurons, then 64, and then 32. After the data is passed through all the encoded layers, you normalize it using batch normalization, send it to the bottleneck containing again variable number of dimensions, and then that data is again normalized. And once that's normalized, you figure out what the mean is of that distribution, you figure out what the log variance is of that distribution, and you also figure out what the latent variables are. This is just used to sample the latent variables for later on. Once this has been predicted, the mean and the variance, you pass them essentially through the decoded layer. So the decoded layer, that we have three of them. The first one uh, having 32 neurons, then 64, and then 128. And once the output is received, we normalize it using batch normalization and pass it on to the output layer. That is essentially the structure of your variational autoencoder. After that, it essentially does the same things as the others. It calculates the metrics, appends them to the table, plots the graph, and we move on. We move on to the sparse autoencoder, which is made very similar to the first one, but in this case, the difference will be that the sparse autoencoder will not contain any learning distribution at the bottleneck, and it's going to get the data, pass it on as usual. But in this case, the one other difference that we've had is that the first encoded layer would have the regularizer of L1. So L1 is used over here so that it can be used for feature elimination. So any feature that might not be considered relevant might be brought to zero. and that's going to help us eliminate that feature and uh, learn only the most important features for the output. Once that's done, again the same thing happens again and again. Your all your scores are calculated, appended to a list, the graph is plotted, and you move on. Then you come out to the denoising autoencoder. So the denoising autoencoder is one in which you essentially send in a corrupted data as your training data, and then that is compared to your actual output. So the autoencoder learns what to ignore from your data or what to chuck out. So that is basically a corruption that's being dealt away with, and it's learning how to replace missing values in this. So the first thing that I did was that I defined a corruption formula, and this formula essentially generates a random number between 0 and 1. And if that number is greater than 0.5, I will replace the corresponding cell's value with 0. Essentially, I'm iterating through all the cells, and at each cell, I'm generating that random number. And again, if that random number exceeds zero point 0.5, that cell's value is replaced with 0. This is essentially my corruption that I'm performing in that data set. After that, we come on to denoising autoencoders. So after that, we move on and we come on to denoising autoencoders. Now, these autoencoders are essentially used to um, so after you've gotten the corrupted function aligned, then you pass that data onto the denoising autoencoder. The denoising autoencoder is essentially used to uh, So after you've generated the corrupted data, you pass it on to the denoising autoencoder, which will once again learn to either keep or remove a few elements as we as that's the purpose of it, and then it's going to do the same thing again, pass the training data through it, and then test it on the testing data. So over here, essentially what we're doing is that we're fitting the corrupted training data as your X input, and you're taking the actual data as the comparison for later on. So this is going to be used for error calculation, and that's the same thing for validation, right? So you're taking the test data as your input, and you're taking the your corrupted test data as your input, and your comparison at the output would be your actual test data. And once all of that is done, again, the same thing happens. Your scores are calculated, plotted on, and the losses are plotted on chart, and you move on. You come out to a vanilla autoencoder. Now, this is basically very similar to the variational autoencoder that we've had in the beginning, but the difference is that again, we are not really defining any activation function for each iteration of the vanilla autoencoder, and at the same time, we're not learning the distribution at the bottleneck. So again, same things are happening over here. You have three layers of encoded to encode the data of 128, 64, and 32 neurons respectively, a bottleneck of a variable dimension, and then decoding it through 32, 64, and 128 neurons. You append all of that into one summary table, and that summary after that you also plot the losses. So at the end of it all, we have defined one function called hyperparams. This is essentially taking in the data set that we want to give it, and it's passing it through all of these different sorts of autoencoders. So we have 7 different sorts of base autoencoders, 7 variational, 7 sparse, 7 vanilla, and 7 denoising ones, each with different hyperparameters, so that we can actually have a better understanding of how each hyperparameter affects the results of each autoencoder for each data set. Once that is done, we come here, we start pre-processing our data. So for data set 1, we saw that these were the columns that we had. We checked out the names of each column. We applied min-max scaling to it, got the transformation over there, split it into train one, test one, and then passed it on to our hyperparams. So these are all the results that were plotted against that. As you can see, the testing data performs very it varies. The performance of the testing data varies quite a lot for variational autoencoders mostly over here. C sparse autoencoder is still very stable compared to that until we come to the sigmoid activation function or the tanh activation function. Other than that, you can see it's very, very similar. One thing I noticed while performing all of these was that our denoising autoencoders were the only ones where the testing data had lower losses than the training data. This was a constant feature throughout all the data sets for all the denoising autoencoders. We've also conducted a bit of analysis over here on our notebook. You can actually read all of this when we upload it onto Kaggle, and the link should be in the description. Dataset 2, same thing. We came here, we dropped the instance and the date day columns, and then we also applied min-max scaling to the rest of the columns, passed it through the hyperparams.